Good day, everyone. Welcome, and thank you for joining the last day of CosmoPalooza 2023. My name is Satya Goncho, and I'm one of the co-organizers and the facilitator for this first session, where we give the floor to the Dark Energy Survey. Let's welcome our first speaker, Agnès Ferté.
Thank you, Satya. Okay.
Perfect.
Okay, thanks. Hi, everyone. Thanks, everyone, for joining. And thank you to Satya and Anthony for organizing CosmoPalooza and inviting us to talk about the Dark Energy Survey. I will talk especially about our latest science and our ongoing analysis. Let me just put my timer on. Okay. So our model of the universe as of today is pretty simple, with a universe that has been expanding since the Big Bang, and the matter density fluctuation created, we think, during cosmic inflation has been expanding over the whole story of the universe to form the large-scale structures that we see today. And we know from many different probes that the universe expansion has been accelerating for the past 5 billion years. And the question DES wants to answer is what is causing this cosmic acceleration? Is it a dark energy? And if yes, what is dark energy? Is it a property of space-time? Does it evolve with time, etc.? Or is it a sign that general relativity needs to be modified? It's not complete on cosmological scales. And in this case, we would need to replace GR with something else to explain cosmic acceleration. So to answer this big question, the Dark Energy Survey builds the DCAM camera and put it on the CTIO Blanco 4-meter telescope in Chile. And this camera is big and has a big field of view with 2.2 degrees. And that enabled us to map galaxies in the southern sky over 10% of the sky, which is one of the largest weak-lensing surveys to date, in 5 optical bands. We detected 700 million objects, and from these images, there is a whole wealth of science that's a whole international team is working on. One of our key science is multi-probe precision cosmology, which I will detail in the rest of this talk. But there is also understanding our solar system and discovering new bodies, mapping surrounding of the Milky Way like dwarf galaxies, but also following up of gravitational waves or detection of strong lensing systems. So regarding cosmology, it happens in 3 phases. First of all, we did cosmology from the first year of observation on like only a part of the footprint, which we released in 2018. And later in 2021, we released the cosmology from the 3 years of observation. And that was the first time we were doing cosmology from the full footprint, the full 10% of the sky. And right now we're working on the analysis of the full survey, the 6 years of observation. So over the whole footprint, but also taking all the several visits of the different parts of the footprint. So there are different ways to probe dark energy. And one historical way is to measure how the universe expansion has been evolving. So to do that, we need to measure distances, which is difficult in an expanding universe. So we need to use different standard scales or candle. So one of the probe is to use TAP 1A supernovae as standard candles. And from the first 3 years of the DES supernovae program, we confirmed 200 supernovae, and combined with the cosmic microwave background, we were able to constrain the equation of states of dark energy. And Patrick Armstrong is going to talk more about this probe and the ongoing analysis, final analysis for supernovae. Bionic acoustic oscillation are another way to probe distances. It corresponds to the oscillation in the early universe that got imprinted on the matter distribution, and it shows up today on a stronger clustering of galaxies at a standard scale. And from the first 3 years of observation, we measured this BAO with 2.7 precision at redshift 0.8. And Juan Mena is going to talk more about BAO and the ongoing last BAO analysis from DES. Alternatively, we can also probe the growth of structures, of matter structures in the universe to test dark energy and gravity. And because most of matter is dark matter, we need to find indirect ways to probe this growth. So first, we can use galaxies as tracers of the large-scale structures, but also as background light, because the shape of galaxies is distorted by structures on the line of sight due to lensing. And we summarize both this information into 2-point correlation function of the shape and position of galaxies at different tomographic bins. And in the end, we end up with 3 types of correlation: cosmic shear, galaxy-galaxy lensing, and clustering. And we refer to it as 3 by 2 point. And with the 3 years of observation, we built the largest shape catalog to date with 100 million galaxies. And from this precise measurement of weak lensing and clustering, we ended up with a 4% precision on sigma A10 omega M, which is shown here compared to results from the cosmic microwave background from Planck satellite. Galaxies also agglomerate in clusters, and by counting the number of clusters and measuring their masses, we get access to the growth of structures. From the first year of observation, we detected 7,000 clusters and obtained cosmology from this observable, which is shown here. And this plot is very exciting because we can show the result on cosmology from all these different probes from the same survey from DES. But focusing on the weak lensing aspects, so cosmic shear was first measured only 20 years ago. So it's very exciting to see at what stage we are at now with DS, but also KIDS and HSC measuring weak gravitational lensing. And one of the results from this year is the combination of DS year 3 with KIDS 1000, and to measure the parameter S8, this combination of sigma 8 and omega M, and test different modeling and analysis choices to see if it could solve the S8 tension between weak lensing and cosmic microwave background from measurements from Planck. And DS is really a precursor for the stage 4 weak lensing surveys like LSST from the Rubin Observatory, which is being built the mountain just next to DES, and also from space with Euclid and the Roman Space Telescope. And all this survey will measure weak lensing with greater precision, with more galaxies and more parts of the sky. But right now with DS, we are preparing for the challenges for these future surveys. And from the 3 years of observation, we went beyond just getting the cosmology. First, we tested for different beyond lambda CDM models, which is an analysis I co-led, and I was specifically contributing to testing for this parameter sigma naught, which tells us about how if lensing acts as expected in general relativity. And overall, over those, so we got the most constraining power on this parameter, and overall, over all the models, we didn't see any deviation from lambda CDM or GR, but we pinned down some challenges that we absolutely have to solve if we want to make the most of LSST, Euclid, and Roman. We also correlated 3x2 points with the lensing of the cosmic microwave background by correlating 3x2 point with SPT and Planck lensing maps. And this is useful to both do consistency test to check our 3x weak lensing and clustering results, but also to get tighter constraints on cosmology. So right now we are working. We are now working on the analysis of the full survey. So going from the images from the whole 6 years of observation to measure 3x2 points and get the cosmology. We are a tight team, and many of whom are early career scientists and very talented, working on the data side as well as on the modeling side. We need both to ensure that the cosmological inference is not biased and robust. I specifically contribute to the modeling, so I just spend one slide on it. So right now, one of our obstacle to get the most out of the year 6 data is the scale cuts that we do in our analysis. We remove data points where we don't trust the modeling of weak lensing and clustering, which is typically at small angular scales where the matter distribution is more uncertain. But with this new precise data, that means that we need to push our modeling choices, like for bionic feedback or galaxy bias. And the year 6 modeling team is developing and applying new approaches to push towards accessing these smaller angular scales while ensuring robust cosmology. So to conclude, you can access the GSGS3 data product at this link. So please use them. There is a whole variety of data products ranging from catalogs to cosmological chains. Right now, we are a lot of us are working on analyzing the full survey and measuring the weak lensing and clustering from these images. And I will let Theo should talk more about the weak lensing part of it. And because I was the co-convener of the theory and combined probe working group, I just wanted to highlight also other work that is ongoing, where we are also thinking about using beyond 2-point statistics to get to cosmology. By using different type of statistics like split peak statistics or bispectrum, also other density properties like void, but also by using machine learning. And in parallel, new cosmology results will come from clusters BAO and supernovae. And to learn more about it, please follow the following talks. Thank you.
Thank you very much, Agnes. I see one first question in the Q&A. Do you have complete observations in all 5 bands, UG, R, I, Z? How deep does each band go?
Yes, we have images from the 5 bands, but we don't use all of them for our science. And I will let Theo maybe elaborate on that because they've done a lot of work on it. And I don't have the numbers for how deep it goes, but yeah, probably on the Dark Energy Survey website, we can find the answer.
Okay, thank you. We might have time for one more question. All right, well, in which case we'll move on to the next speaker. Thanks again, Agnes. And then now, next speaker is Theo Schat. If you want to share your screen, and you have the floor.
Yeah, thank you, Satya. Okay, thanks everyone for having me. So I'm going to be talking on behalf of the DES-Y6 Shear Analysis team to talk to you about the 2 weak lensing shape catalogs that we are currently building. So before I get into the catalogs themselves, I want to go over how we get from shapes to cosmic shear. So for each galaxy in our survey, we do an observed ellipticity. And so this is a combination of the intrinsic ellipticity and the lensing effect shear. And so the lensing effect is about 1%. And then our estimator includes these systematic effects, so multiplicative bias M and additive bias C. And so cosmic shear is the process of taking a two-point correlation function of these observed ellipticities. And so we have the shear component as well as our additive biases and this multiplicative factor. And then what you will see in literature is the conventional decomposition of Xi plus and minus. And so this decomposes the ellipticities in terms of what's tangent to the line connecting two galaxies, which is this ET, and the cross component, which is along the line connecting the two components. And so the positive and negative correlation conventions are shown here. So for the folks who are actually making these shear catalogs, we have a lot of early career scientists working on this, as well as many senior members. And so we have some main data products that we are creating. First are the PSF models that are for each exposure in CCD, as well as a reserve star catalog for validating these. So that's the work that I've been leading. We have two independent shear estimation methods, meta detection, which is being led by Masuya Yamamoto, as well as the Bayesian Fourier domain method, BFD, which is being led by Marco Gatti and Vernon Wetzel. And then to do shear multiplicative bias calibration, we'll have 500 degrees squares of realistic image sims. And so this is being led by Sydney Mao, Fox Davidson, and Alexander Tong. So the first step in making these catalogs after we have calibrated images is making the PSF models. And so we use this software called PIF, PSFs in the full field of view. And so for Y6, what we do is we measure a point spread function solution for each CCD in the field of view. And then, yes, so these go into the shear catalogs later. So the same method was also used in Y3, but there are some open problems. So the first major problem that was found was that we did not include color dependence, and this is expected to have cause issues for the PSF. And so for this plot on the top, this is showing the residual in the ellipticity component E1 versus what we call the differential chromatic refraction angle 1. So this is an effect that spreads light towards zenith. And so this is a way of isolating this effect just for E1. And so we see the top 25% bluest stars and top 25 reddest stars show this bias due to DCR. Similarly, our optics can also cause issues with chromatic aberrations. And so this plot is showing a size residual of our PSF versus the focal plane radius going from the center of the focal plane out. And we see also that the bluest and reddest stars also show significant residual due to these chromatic aberrations. And both of these effects happen the most in bluer wavelengths, so they affect our G and R bands the most. A second issue was that there was possible galaxy contamination of our input stars. And so this can bias our PSFs if we're not using point sources to make the point spread function. So these combined led to the fact that in the year 3 weak lensing analysis, we did not use G-band data, and so only used RI and Z. But for Y6, we've made a few major improvements. The biggest improvement has been including color dependence modeling. And so you can see on the right here is the Y6 measurement of this differential chromatic refraction effect. We have like significantly decreased it compared to Y3. Similarly, chromatic aberrations are also taken into account for this color dependent modeling. And we see that this is also significantly decreased versus Y3. Second, to refine the star galaxy separation, we've included IR photometry because now we have a very large coverage of IR data over the DES footprint. And so now for Y6, we will be using G-band fluxes for photometric redshifts, which we've shown can help with defining our redshift bins and separating our N of Z distributions. So the PSFs are a major data product that go into how we measure and calibrate shear. So I'm going to go over the two methods that we will be using in Y6. So the first is meta detection. This measures shapes on single band multi-epoch coed images. And so in the name, the meta refers to that it calibrates the shear response using the data itself. We don't make any assumptions on the galaxy properties. And then the detection part is that detection is now included in the shear measurement to calibrate for the shear dependent bias that comes from detection. And so this part is actually new for Y6. And so the detection happens on a cutout of a 200 by 200 pixel square, and then shear measurements are made for each detected galaxy. The second method is Bayesian Fourier domain, or BFD. And so this is a completely independent measurement of shear. It measures shapes on single epoch images for galaxies. This is totally new for Y6. And so the method compares target galaxies from the wide field survey to an unsheared population of basically noiseless real template galaxies from the deep fields, compares their moments and measures shear using those. And so the first catalog meta detection is very far along in its validation process. And so some very preliminary statistics is that we have about 150 million objects, which is 50% more than Y3, with an effective number, galaxy number density of 8 galaxies per minute squared. There's a low shake noise of 0.27, leading to a shear precision that's 16% better than Y3. And so this is a map of our weighted number density over the footprint. And these are a couple of null tests that we are passing. So this is the null test of shear over the CCDs, as well as shear as tangential shear around the cell centers. So those are the 200 by 200 pixel squares. Coad centers, which are large 10,000 pixel by 10,000 pixel coads, and around field centers, which is our, for each pointing, we measure tangential shear. And then our second method, BFD, is at an earlier stage of validation, but we still have the catalog. So the preliminary statistics here, we have much more objects in BFD. So it's 212 million objects, which is about 40% more than this meta-detect catalog. So it's a higher galaxy number density of 13 galaxies per arc minute squared. but this BFD doesn't go quite as deep, so the shape noise is higher with 0.032 or 0.32. But the number of galaxies overcomes this higher shape noise, so the shear precision is about 10% larger than the MetaDetect catalog. And so this on the right here, showing the galaxy number density over the footprint, as well as the standard deviation or shape noise. And so in conclusion, 3x2 point requires very high precision measurements at the pixel level. So we've made a lot of major improvements from Y6 to Y3 to match the statistical precision that we have from this new data. The major improvements has been including color dependent or chromatic PSF modeling, 2 new completely independent shear measurement methods, and as well as expanding our image simulations to take up 2.5 times more sky area than Y3. And so our progress, BFD validation is continuing. It's very successful so far. We're ramping up our image simulation processing in order to calibrate both MetaDetect and BFD. The PSF validation is essentially complete, and MetaDetection validation is also nearly complete. And so those are some main successes for our group. And we're very excited to be sharing these catalogs in the near future. So thank you.
Thank you very much. Let's have a look and see if we have any questions right now in the Q&A. I don't see any. Okay. Is there any coordinated effort maybe with other maybe not collaboration, but you know, for in seeing future surveys scope, do you have coordinated efforts maybe between different groups or different, you know, collaborations? Because I know people are in both, but
yeah, that's a great question. So many of us are also in DESC, so the Dark Energy Science Collaboration for Rubin. And so a lot of the software that we're making for the DES-Y6 is also going to be some of the default software for the LSST. And so this PIF, the PSF software that we're developing, is the default software for DESC, as well as MetaDetection is also implemented within Rubin's data management. So there's been a lot of collaboration in terms of things that are definitely useful for DES, and looking forward to the next generation of surveys.
Okay. Another question we had is there a scientific reason for choosing that particular patch of this in the sky to carry out your analysis?
Yes, so the dark energy survey footprint, which I can show maybe, is placed, the telescope is in the southern hemisphere, so it's in the south, and it's mostly placed so that it avoids the galactic plane. So we want to get as deep as possible and avoid stars so that we can maximize the number of galaxies we can use. And so that's how the footprint is placed.
Thank you. We are at time. So Theo, thanks again. And then we'll move on to the next speaker, that is Juan Mena.
Okay, can you see the slides? I guess you can.
See your slides, see full screen, see everything. You're good to
All right, I will start. Thank you, Satya. So thank you very much for having me here. I will talk on behalf of the LSS working group of DES about the measurement of the baryon acoustic oscillations using the DES-Y6 data. First of all, a bit of an introduction. Several things here. First of all, the sample, the sample that we use to measure the BAO is re-optimized with respect to the Y3 analysis. In particular, we also have one more redshift bin compared to the Y3, which goes from 1.1 to 1.2. The reason being we have deeper photometry, so we also have better photosys. Regarding redshifts, our fiducial redshift distributions use information from DNF, which is our photosy code, Viper's spectroscopic redshift, which is a spectroscopic sample that has an overlapping region with DES, and also clustering redshift. Regarding estimators, we provide BA measurements from 3 different statistics, which are angular correlation function, or W theta, angular power spectrum, or CL, and the projected correlation function as well. And then what we do, the fiducial result, is a combination of the 3 of them. Also important, the analysis is performed blind, and we require our data passing a battery of robustness tests before unblinding. And for you to know, we are currently close to unblinding, but since it's not unblinded yet, I will not be able to show the cosmology results, but I will be able to show you other things. The first thing in the analysis, of course, is to have the sample that we use to measure the baryon-acoustic oscillations. And this is how we perform the optimization of the selection cuts. So we run forecasts to estimate the uncertainty in the position of the BAO peak that I call sigma BAO. The sample selection that we use is very similar to that of the Y3, where we have these selection cuts, and we have 2 free parameters here, A and B, which are in the I magnitude photosy dependent limit. These selection cuts are applied to the Y6 called catalog, which is the catalog that has all the DES galaxies. What we do is to run the optimization as a function of A and B, as I said, in these ranges of A and B. And in this matrix here, you can see the values of sigma BAO as a function of A and B. So each point in this plot is a different sample. We have to select that sample, we have to run the forecasts and everything. And here you can see 100 by 100, so a total of 10,000 samples. And the red point here is a sample that has the lowest sigma BAO. And its optimal parameters, you can see them here. So A, 19.64, and B, 2.89. And these are the Y3 values as reference. And in this table here, I want you to focus on this line here, where we run the forecast for the Y3-like sample, and we obtain something like 2.1% error. And for the Y6 optimal sample, for this sample here, we obtain a 1.6% error. So if you compare these two, we expect an increase in precision of around 25% in the Y6 analysis with respect to the Y3. Here you can see the main properties of the BA sample, of the optimal sample we just selected, compared to those of the Y3. So this is Y3 and this is Y6. You can see the different redshift bands, the number of galaxies, and the sigma 68, which is basically the dispersion of the photosy. It's a measure of the quality of the photosy. So the lower, the better. And all right, then we have, if you compare, we have almost 2 times the number of galaxies, but that's because the selection cuts are different with respect to the Y3. The effective redshift, of course, is larger in the Y6 because we have 1 more redshift bin, as I said before, and the area is pretty much the same. So as a summary, with respect to the Y3, in the Y6, we have around 2 times number density, better photosy accuracy, also narrower redshift distributions, and 1 more redshift bin. Now that we have our sample and we know the properties, we have to measure the clustering or the clustering measurements. And in order to do so, we have to first mitigate systematics. And these are mitigated with the iterative systematic decontamination algorithm, which is the algorithm used in the DES-Y3 analysis, and it's described here. So we basically have linear weights with up to 3 systematic maps out of 17. For you to know, angular correlation function, angular power spectrum, and projected correlation functions were already measured on our Y6 sample. However, they are blinded, so we cannot plot them, but we use them, as you'll see later, in a blinded way. However, for the angular correlation function, 3 data measurements below 1 degree are allowed to be used before unblinding in order to calibrate the simulations, as you will see now. So we need simulations for several things, including validating our pipelines and also running the pre-unblinding tests. And what we do is to generate a set of almost 2,000 iScholar mocks with the same properties as the Y6 sample. The methodology is described here. And here, what I show you are the angular correlation functions, or W thetas, for the different redshift bins, as you can see, for each mock individually, the black lines, and also the average, which is the red line. And you can also see something that says pre-unblinding data, which is what I mentioned earlier. We are allowed to measure this on the data only to calibrate the clustering on small scales, but this does not have any information on the BAO, which is typically at much larger scales. So, yeah. how do we extract the BAO information from our clustering measurements, in particular from W theta? So we use a template-based method in order to measure the position of the BAO peak. The model is given by this expression here, where, of course, the model goes into the chi-square as data minus chi-square, covariance, and so on, data minus model, covariance, data minus model, and the covariance we rely on analytical covariances computed with CosmoLight. Then the model has several different things here. We have an amplitude parameter that multiplies a template. The template is where the physics is encoded. And in order to compute a template, we have to assume a fiducial cosmology, as you'll see now. So the template is obtained integrating the power spectrum and then projected in Redshift. And here in this part of the slide, I show you the model that we use for the power spectrum, where we have a Kaiser term, we have the linear power spectrum, the no-wiggle. We also have a term that takes into account this exponential, the beer dumping, and you also have the no wiggle here. So this is power spectrum, and what we do then is to compute the Fourier transform of this, which is the 2-point correlation function, and then the 2-point correlation function is double integrated in Redshift, taking into account the Redshift distributions of our sample in order to compute W theta in this case. So this is the way we compute W theta from the theoretical power spectrum. Then alpha that you see here is the BA shift parameter, which basically measures the position of the BA peak of our template with respect to the data. So it's given by this expression here, where we have the comoving angular diameter distance divided by the sound scale horizon, and this same quantity divided by, this quantity divided by itself, but evaluated at the fiducial cosmology that we use. In this case, it is Planck 2018. So basically, when we run our pipeline, we measure alpha, and we can then solve for this quantity because this one is known, because we know the fiducial cosmology that we used. And then the broadband term parameters that are here that are used to fit for small differences between our data and our model W thetas. First test we did with our sample, is the BA detected? And the answer is yes. However, measurements are still blinded. We cannot check the actual value of alpha, but we can check if we have a detection or not. And what we found is that we have a detection when fitting all the redshift bins together for the 3 different estimators that we use: angular correlation function, angular power spectrum, and predicted correlation function. And when we fit each redshift bin individually, we find a non-detection in the first redshift bin for the 3 estimators. And here you can see these numbers are the probability of finding a detection in our simulations, in our 2000 simulations. However, so we have a non-detection in the first redshift bin, which goes from 0.6 to 0.7 for the 3 estimators. This is not surprising because we already found this in the Y1 and the Y3 analysis. And also, this is not weird because this is consistent with the simulations. For example, for angular correlation function, around 23% of the simulations have a non-detection in one redshift bin. So it is not surprising that we have a non-detection in one of them, and we have detections in all the other redshift bins. Now, talking about the pre-unblinding tests, we have lots of tests that we run, in particular for the individual estimators. For example, we remove each redshift bin individually. We compare high C results versus low C. We change the cosmology of the template. We change the covariance for the fits and also change the redshift distributions. And for each test, what we do is to compute delta alpha, which is the alpha fiducial on the data that we cannot see that value, but we can compare the difference with respect to a variation in the analysis. And we do this for each of these variations in the analysis. And then what we do is to compare this delta alpha with the delta alpha measured on the mocks. We check if it lies within the 90% interval from the mocks. We also run tests when combining the estimators. So we combine it in a way that these weights that you can see here take into account the covariances between the different estimators. And in this table, what you can see is delta alpha, for example, angular correlation function minus angular power spectrum and the other 2 combinations, and also the combined result minus each of them individually. And what you see here, these results from the data, which are, again, they are blinded because they are just differences, not absolute values. They lie within the 90% interval of the mocks. So basically, we pass every test and everything looks very good. We also pass these tests. And basically, we found that our measurements are consistent with results on simulations and our data is robust. And we pass the pre-unblinding tests. And what do we expect for the Y6 in terms of a measurement? So here you can see the BA distance ladder, including results from BOS, EVOS for different tracers, and also including the DES-Y3 measurement here. What we expect for the Y6 is a measurement at a slightly larger redshift. It's going to be the combination of the three estimators that I talked to you about, and we expect around a 25% smaller error. We don't know where the DES-Y6 data point will be, because it could be here where the DES-Y3 is, and we know that the error bar is going to be smaller. So this is just a forecast. We don't know if it's going to be here with perfectly consistent with Planck or not. And now, as conclusions, the selection cuts have been optimized with respect to the Y3, and we expect an increase in precision of around 25% in the measurement of the BEO scale. Our measurements on the data pass the pre-unblinding tests, and unblinding will happen soon, so stay tuned for that. And yeah, just as a final remark, the DES-Y6 analysis will provide the most precise BEO detection from a photometric dataset ever, and it will also be competitive with current results from spectroscopic surveys at our effective redshift. And that's it. Thank you very much.
Thank you very much. You have a few questions, so let me start. What model do you use to forecast the BEO uncertainty? And then there's a follow-up question to that. How do you connect your A and B parameters, those enter the I-band cuts to the BEO model? Okay, so the forecast we use are Fisher forecasts. So we simply kind of compute like the derivative of the power spectrum with respect to the position of the BEO peak, and then integrate that. And all right, how do we connect the A and B parameters? So what we do is to apply these selection cuts to the gold catalog, and that way we have a sample. Then for that sample, we compute, like, for example, the number of galaxies, the photo C quality, or sigma 68 that I talked to you about before. For each sample, we do that, and those are the quantities that goes into the forecast. And from that forecast, for each sample, we compute the sigma 68. Hopefully that clarifies. All right, thank you. Another question is, what is the redshift range for which the photometric redshifts of DES is reliable? And how reliable are the photometric redshifts for fainter magnitudes? Yeah, all right, that's a good question. Up to 1.2, which is the one that we are taking now, we are pretty sure that we have good redshifts, because we can measure that with our photo C code, and we know the training that we are using. We know we can go up to that. But for the magnitude limit, we cannot, in this case, we have this magnitude limit of 22.5 because our training samples, spectroscopic training samples, do not have fainter magnitudes. So therefore, we would not be able to validate or trust those photocies. But indeed, the DS catalogs have magnitude deeper than this. But because of that, we cannot use them because we would not be able to validate the photocies. Those galaxies. Okay. Last question is, aren't the three estimators highly correlated? How much do you gain in the combination? Yeah, that's also a good question. So yeah, they are correlated. For example, if I remember correctly the numbers, angular correlation function and angular power spectrum was something like 85% correlation. An angular correlation function and projected correlation function, for instance, was like 90%. So it's not, I mean, it's high, but since it's not like 100%, combining gives you a little bit of a gain. And actually, we tested that on simulations, and we found, for instance, that the combined result is more Gaussian than the individual ones, the individual estimators. So we gain a little bit. We also gain a little bit in the error bar, not too much, but a little bit. Okay. Well, thanks again for this talk, and we'll now move on to the next speaker, Patrick Armstrong, who is giving his talk at 1 in the morning. So thank you so much.
No, don't worry. Yeah, so as mentioned, I'm Patrick. I'm a PhD student with the Australian National University, and I'm here today to chat about the supernova side of the Dark Energy Survey. Super exciting. This year we unblinded, which is really cool. We're writing up the analysis papers now. So what I want to do is go over some of the things that have changed in our methodology between the 3-year results and these new 5-year results, and then show you what I can of the 5-year results. I can't show you everything. We're still making sure everything is correct, but there are some things that I can give you. So just to start, I want to briefly go over what we're attempting to do in supernova cosmology. As I'm sure you're all aware, 1As are standardizable candles, which means we can measure the distance modulus as the difference between the apparent and absolute magnitude plus some standardization parameters. Additionally, cosmology theory gives us another way of calculating the distance modulus based off the redshift and a number of cosmological parameters, including the omega parameters and the dark energy equation of state parameter. And so the goal of supernova cosmology is to find what cosmological parameters will mean that the theoretical distance modulus and the observed distance modulus match. Now, in the dark energy survey, we standardize our light curves using the TRIP metric, and we do this through the SALT framework. So the idea behind this is that the standardization is a combination of a parameter called stretch, which is roughly analogous to the width of your light curves, and another parameter called color, which is related to the difference between different filters of your light curve. In addition, there are a number of nuisance parameters, such as alpha and beta. These cannot be calculated a priori. They need to be fit alongside other cosmological parameters. And in addition, we also accept that there will be some contamination and observational biases in our data that we need to contend with as well. So getting into the meat of it, the way that we do this supernova cosmology in the dark energy survey is through a pipeline known as Pippin. This is originally designed by Sam Hinton and has since been taken over by myself. So what I want to do is go over how Pippin works and also highlight some of the changes between the 3-year and the 5-year methodology. So the very first step is taking the raw data and extracting the supernova light curves from that. In the 3-year, we mostly use difference imaging for this, but in the 5-year results, we're now using scene modeling photometry, which is a more computationally expensive but much more accurate method of extracting light curves. We also do simulations using the SNANA code. These simulations are used to validate the various programs that we use in our pipeline, as well as being used for correcting observational biases. The next step is light curve fitting. This makes use of, like I mentioned, the SALT framework. And SALT got an update between the 3-year and 5-year from SALT 2 to SALT 3. This made it much easier to work with. It increased the wavelength range and increased the number of supernova in our supernova models used for the training. So big improvement there, which is fantastic. The next step is to classify all of our supernova to attempt to remove any contaminants. In the 3-year, we use spectroscopic classification. This is headed by the OSDES group, which is a group here in Australia that did most of the spectroscopic follow-up. For the 5-year, as the number of supernova increased, we've since moved to photometric classification. This is using the Super N Nova or the SCONE photometric classifiers, which are both some fantastic machine learning algorithms that were built for this purpose. Now, once we have the classifications and the light curve fits and the simulations, we're able to start correcting our data for contamination and observational bias. And we make use of the BBC or beams with bias correction method for this. One of the big changes here is the scatter model that we use. Previously, we assumed G10, but we have since developed better scatter models that seem to match the data much more realistically. The output of this stage is a Hubble diagram that is corrected for both contamination and observational bias. Because of this, we are now able to start handling systematic uncertainties. We do this by building a rather large covariance matrix, which then gets combined with the Hubble diagram for the cosmological fitting stage. And here the main change is the cosmological fitter we are using. We used to use CosmoMC, but have since upgraded to Cosmosis, which is a more sophisticated fitter that gives us a lot more play with the different models that we are trying to fit. So that's a fairly brief overview of the pipeline that we use and the changes between 3-year and 5-year. There are a lot more changes that have happened behind the scenes, but this talk is only 10 minutes, so I can't really go into it. What I want to do now is start looking over some of the results that I'm allowed to share with you about the 5-year data. The first result I want to show here is just the sheer volume of supernova that we have. On the left, you can see both the low redshift and high redshift samples that are used in the DES supernova 5-year analysis. The gray in the back is the Pantheon Plus survey, which was the previous largest survey that we could compare to. I'll just quickly note that this is a zoom in of this plot here, but the axis has changed from a logarithmic to a linear, so that's why the shape of the distributions are slightly different. But the point here is that at the moment, 80% of the supernova above a redshift of 0.4 come from the dark energy survey. So we are heavily contributing to the number of high redshift supernova. And this is only photometrically classified supernova. This isn't even including all the spectroscopically classified ones that we have. We also, as I mentioned, unblinded, which was very exciting. There's a lot of work to get to passing all of our unblinding criteria. So I just want to go over what those were. The biggest one that changed between the 3-year and the 5-year was the changing of the requirements on the quality of the simulation. So the very first unblinding criteria is simply making sure that we are recovering an input cosmology. We simulate with some known cosmology, and then we see if we get that cosmology back. And the average difference between the best fitting W and the true W is appropriately small over 25 simulations. Pardon me. The next requirement for unblinding was ensuring that our simulations were realistic and of high quality. And the way that we did this is we picked a number of population parameters that we felt were important to recover and ensure that our simulations were matching our data in all of these to some appropriate level. There was a huge amount of effort across the DES Supernova team to get the quality of these simulations up to the scratch that they are at the moment. The next unblinding criteria is just ensuring that when we do our cosmology fit, the chains actually converged. And then finally, there was some work that I did this year of developing a method to validate our contours, which I don't have time to go in, but I'm happy to chat about offline if anyone is interested in it. So now to get into the meat and potatoes and show you some of the cool results that we're allowed to show. So just for comparison, this bottom plot here is the Hubble diagram for the 3-year data. This one up here is a preliminary Hubble diagram for the 5-year. And over on the right, I have the statistic and systematic uncertainty budgets without any CMB prior, and then the statistic and systematic uncertainty budgets with a CMB prior. This is just for the DES 5-year. So the first thing I really want to point out is that the number of supernova has gone from 200 to 1600. So we've increased by an order of magnitude. And as I mentioned, for the 5-year, we are only using the DES photometrically classified supernova. The reason for this is we want to test whether this actually produces a good result, because there's a belief that once you get to LSST, photometric classification is going to be the way forward. It is certainly possible to include the spectroscopically classified supernova in this as well, but for these first set of key analysis papers, we're focusing on the photometrically classified. The next thing I want to point out is that the uncertainty that we're predicting for the 5-year results is about a factor of a half of the 3-year results. So we're improving on our uncertainty quite a bit. And importantly, we're not yet systematically dominated. We still have a good chunk of uncertainty that is statistically dominated. So there's still a lot to be gained by increasing the number of supernova that we have in our samples. The different colors of the systematic bars show the different sources of systematic uncertainty. And at the moment, the major sources are the SALT model that is used and the scatter model that is used, the dust model that is used. So those are areas that can be looked at for improving systematic uncertainties. And yeah, that's all I really have to say. Quite quick and short. But we've unblinded, which is fantastic. We've got a number of key papers, including the analysis and the results papers in preparation. These results will include an order of magnitude more supernova than the 3-year results, and we're expecting a reduction in our uncertainty by a factor of 2. So thanks for listening. Let me know if you have any questions.
Thank you very much. Let me check if there's already some questions written out for you. I don't see any at the moment. Is there anything else you want to maybe that you're excited about or that you want to tease?
Yeah, so I think there's a number of very interesting problems that we tried to solve. One of the ones that was very tricky for us is whether to bin or unbin our data. In the 3-year, there was a good amount of work in fitting a bin tupple diagram where you're binning by redshift. But we since discovered in a lovely paper called Binning is Sinning that binning your data can introduce a bias in your results. And so there's been a lot of work on trying to understand why that is and to find a solution to this problem. That means that we don't need to waste the time on having a 1,000 by 1,000 matrix rather than a 20 by 20 matrix of our covariance matrix. And that was work that was mostly headed by Rick Kessler and Maria Ansfetti over here. So that was quite an interesting thing to take part in and see what's happening. And we talk about that in the papers as well.
Okay. There's one question that says, what is the most important factor to reduce uncertainty? The number of supernovae in the sample or new SALT? And I'll add to that, I know a new version of SALT was something called sugar that was developed. And so I'm wondering if, any of this has been...
Yeah, absolutely. I think at the moment, as we are still statistically dominated, there's still a lot to be gained by adding new supernovae. But especially when you're including a C and B prior, the gap between statistic and systematic uncertainty is closing. So if there are improvements that can be made in the SALT model or in the scatter model, there's the now infamous mass step that is being investigated. That is certainly a cause for some part of this systematic uncertainty. I think especially once we start getting into the next era, the LSST and Euclid era, the statistics uncertainty is just going to plummet, and a lot more effort is going to need to be placed into these systematics to try to shrink them as much as we possibly can. As for the different SALT models, I haven't heard of sugar myself. I know that there's still work done on trying to improve the SALT models. There's a group in Australia that is called the DBAS group that is doing spectroscopic follow-up for the DBAS program in America that is run by Dylan Brout, which is aiming to get a low redshift sample using the same telescope that the high redshift sample used, which will severely reduce the number of systematics we need to handle because we're not trying to convert all of these different, CSP and pan-stars and whatever supernova all to the same magnitude reference frame. And so there's lots of effort trying to reduce every single one of these sources of systematic uncertainty.
All right. Thank you very much. With that, we are at time. So thank you very much to all of the speakers and for DES for putting together this session. Now we'll reconvene in half an hour for the final session of CosmoPalooza on the dark energy spectroscopic instruments. So we will see you all in 30 minutes. Thank you.